So we'll go ahead and get started, go right back to it, and start here. Talking about high efficiency gas furnaces again. Now, this is what I was saying before we left to look in your book on page 872. This has got it where it goes into more detail about the differences of these types of furnaces. So conventional furnaces, again, 78 to 80% AFU rating, mid efficiency 78 to 83, high efficiency 87 to 97. The biggest thing here is this percentage number, all right? Whether it's 78 or whether it's 97%, what you have to understand is what that percentage stands for. What it's saying with that is 50 or 90% or, let's see. Get people, there we go. Cool. Go back to that. So when we have the high efficiency furnaces and everything like that, the whole idea is the percentage number is to explain to the consumer basically how much of this fuel by a percentage is being used for heating, and that's all that means. All right. The rest of the percentage, so it says 78%. Well, what's the other 22? You know, I love, there's a joke, someone, I can't remember what show it was, but it was like, they were talking about how they've been drinking 2% milk. They just don't know what the other 98% is. And so I think for us, we do know what the other percentage is. So the 78% is how much of the fuel is being used for heating. And then the leftover, which would be 22% of that fuel is exhausted or forced out of a building through ventilation. So that's what we're seeing for that AFU rating, what it means. It strictly is talking about the percentage of fuel being used for heating, and then the leftover out of that 100%, that 20% or 22, or for the really high efficiency ones where it's only 3% is left out, then only 3% of that fuel is leaving the building without doing any work, basically, without doing the job that we want it to do, which is to heat our structure. But because we have it where we're dealing with really high efficiency systems and everything like that, you've got it where now you're having less and less of a percentage of it is going out of the building, out of the structure. More of it is being held onto. We're holding on to it longer. We're keeping it in the structure. And that makes it so that we can, if we're holding on to the heat longer, we're going to produce more heat in the building before it gets out of the building. So we've got it where, because we're producing extra heat, we can actually have, we can use less fuel to heat the same space, to heat the same square footage, to heat the same floor plan and everything like that. Just by introducing a higher efficiency system, you've got it where it's going to be really, really high efficiency as far as the okay, that's how it works. Okay, cool. I'm trying to figure out the best way to get this thing to do its deal. Again, high efficiency systems we're talking about 78 to 80% is going to be your low, but high is the 87 and 97. Most of the time, most people will call it 90 plus furnaces, or they'll call them 90% furnaces when they're talking about high efficiency ones, because it's got that plastic flue piping. As soon as you see that, you know it's somewhere between 87 to 97, typically 90 to 97. That's more often what most people consider high efficiency. Starting at is 90, not 87. Just because sales numbers and things like that, people will call it different ways. But most folks, in my experience, what it's been is if you've got a 90% furnace, that's when you start dealing with high efficiency. So your book explains there's a lot of differences between these systems, between a conventional, a mid efficiency, and a high efficiency. The big thing is you've got there's something in there they talk about called the delta T. So the delta T, what it's talking about when it's explaining that is you've got it where that's the temperature rise across the heat exchanger. So we have our fan motor, all right, and then above that we've got a heat exchanger, and the air goes up across that heat exchanger. Now the delta T is the temperature difference between before and after it goes across that heat exchanger. Before it's heated and after it's heated. What we do is we take a measure of the temperature of the air, and we actually see, okay, how cold is the air coming in? Let's say 70 degrees, or well, honestly, if it's wintertime, 65, 60 degrees, it's coming in. And then we have it where we check going out after it passes across that. It goes from 60 to all of a sudden it's, 120. And that's a 60-degree difference. We've just increased that air temperature by 60 degrees. So that's what we're talking about when they're talking in the book about the delta T and everything like that. That's going to be you having it where it's just how much heat are we actually adding to this air by measurable temperature. Not talking about latent heat or anything like that. This is simply 100% sensible heat temperature difference. So a couple other differences that you guys will see throughout that. The only thing I think that's really unique, I guess, to or the big difference as well, besides the delta T, you're going to see is also stack temperatures. All right, and it's going to say stack temperature. Stack temperature, you know, is for a conventional furnace, you've got it where it's going to be about 350 to 450 degrees Fahrenheit. This is going to be about 275 to 300 degrees is the mid efficiency. And then the high efficiency is only going to be about 110 to 120. Some of them I've seen where it gets down to 90, you know, below that and everything. Let's see. How do I? What's going on, Dominique? Oh, let me see if I can get this thing to. Ooh, how do I get it? I can't. Yeah. Is your audio working? I'm not hearing you. I see you have the raised hand and the thing. I don't know if that was on purpose or not. Because I can see you, I just can't hear you. Oh, there we go.
Okay.
Gotcha. Okay. All right, so where's that? Okay, so when it talks about flue stacks and flue temperature, it's just another way to talk, or stack temperature and flue temperature, or flue piping, or your flue gases, same exact thing. They all are the same thing. The stack temperature is the temperature of the flue gases in your flue stack or your flue piping to get that air out of there. Now, this is why you have, as you guys look, you're going to see the higher the efficiency, the lower the stack temperature. And the reason for that is because the stack temperature is the byproduct of our heat producing process of the, you know, of combustion and everything like that, where we've got our burners burning. How much of that heat we hold on to will affect how hot that gas is by the time it's leaving the building, right? Because when it gets to the stack, that's at the end of the journey. It's already done all of its heating. It's heated up every part of that heat exchanger as much as it could. It's not going to be doing anything more. It's just going to go right out of the building. But we have it where the more we cool off, more heat that we get out of that system, then we're going to have.
No, you just click the jank, right?
Oh, there we go.
Say,
Oh,
I got you now, Dominique.
I know.
Cause I gotta do my online groups and shit for drug court. He can't hear me, can
I can hear you.
he? Yeah, muted.
Huh?
Yeah. Did you have any questions about the heat exchangers or anything?
No.
So we've got it where the more heat that we're able to hold on to, that's going to cool off that flue stack, and that's why you're seeing, if you look in your book, you'll see it's about 350 to 400, that really high temperature here, and then by the time it gets to this high efficiency system, you're seeing where the temperature is 110 to 120. I've seen some of them where it's as low as 90 degrees. It's how hot the flue gases are coming out of the system. So it really makes its big differences when you start looking at that rating. You'll see a correlation or pattern between flue temperature and then your efficiency level. Those two are related to each other. So if you have a really high efficiency system and you check the flue temperature and it's outrageously high, you know you've got a problem in your system. Somewhere your heat exchanger is not actually absorbing heat like it should be. You could have a problem with some ventilation. You could have problems with tubing. You could have some area or your part of your heat exchanger that got clogged or backed up with byproducts from, maybe it could be they had bad combustion from the beginning. You know, over time, bad combustion can lead and cause a lot of different issues. If we have where we've got too much fuel or not enough fuel, or too much oxygen or not enough oxygen, or we have poor combustion air quality, let's say the room where it's in is in a basement that's very, very moist, or it's in a crawl space and it's taking in crawl space, unconditioned crawl space air all the time, and it's in a, and it's, you know, there's not a good vapor barrier, there's a lot of water down there. That can cause a lot of issues. I've seen it before where I've gone in to find a 90% efficient system that's not working simply because the combustion air it was taking in had basically clogged up all the burners. Everything that was burning was really high humidity because it was in that crawl space. It had high humidity in that crawl space, and that made it so that the combustion, all right, one of our byproducts is water vapor, but this, because it was so moist, the water vapor started condensing basically on the ends of the burners, and your burners were covered in just rust, and that's what happened to that system. So there's a lot of different ones that you're going to see, but those two things right there, the efficiency rating and the flue temperature, are always going to be tied together. And you should see pretty standard stuff when it comes to it. All right. So electronic ignition control modules, we've got basically one used nowadays. All right. Used to be back in the day, you would have a lot of different systems of controls. You'd have sequencers and relays and contactors. You'd have a mechanically controlled gas valve that would need a pilot light. All these different things we've talked about already. We've talked about how you can use those temperature sensing bulbs, how you had it where it was a bimetallic switch or some sort of electrode or a thermocouple or a thermopile, all these really old mechanical components and everything. For the modern system, however, though, with electronic ignition, the controls are no longer going to be from a mechanical perspective. It's not going to be relying on a pilot light to ignite it. It's not going to rely on a gas valve to automatically open because a signal was sent via a pressure change or something like that. What it's going to rely on is integrated furnace controllers, IFCs or IFC boards, pretty much a control board. All right, that's all an IFC is, or an electronic ignition module. It's a fancy way to say control board. And these are what we're going to see used pretty much in all aspects of heating and air conditioning nowadays, for furnaces, for air conditioners, for systems that are tied together with an air conditioner and a furnace, which is very, very common, especially in Virginia. These are having it where they have it where everything's wired in together. Basically, instead of relying on a lot of different little safeties, we've got a few really good controls and switches. We've still got pressure switches. We're still going to have temperature switches. We're still going to have a flame rectification device or something like that. But the difference is going to be in how the system is actually going to be reading that that signal and everything like that. Instead of it sending a pressure switch or a thermocouple or a flame rectification, control back to, let's say, a relay or a gas valve or something like that, this sends it back simply to a board. And the board's got, it's got relays built onto it, those little black boxes that are on all those control boards we have in the lab. Those each are a relay. And then you've got resistors that are built onto them and all these different little tiny things. The main thing to understand with these control boards is do not jump to the conclusion, oh, it's the control board. The last thing you want to do is think it's the control board. It should be the last electronic part to fail. Now, control boards are pretty easy to inspect and look into. First thing you want to do, and this may sound, well, duh, visually inspect it, all right? And what I mean by that is don't just look at it, scan that thing. Go over it with a fine-tooth comb. Take a flashlight, look over every inch, every square centimeter of that board. What you're gonna look for is black and brown and charred burn marks all or anywhere on that board. If you even see one burnt resistor, one burnt section, one charred little piece of that board's toast. That board's done. So just get a new one. It makes your life a lot easier, all right? So visual inspection, that's the easy one. The harder option is what's called black boxing, all right? You check and make sure that voltage is coming into the board, both 120 or 240 high voltage and your 24 volts of your control signal and everything like that. And then basically what you're gonna do is you're gonna check and make sure, okay, the board's got the power coming into it. Is it sending the power out where it needs to go? It either is or it isn't. All right. If it is sending power to where the board is sending power where it needs to go, then the board is working correctly, and it's something else is the issue. But if we have it where you have the board is receiving power, let's say 120 and 24, that's the easiest and most common you're going to have for residential. You get your 120, you get your 24 volts, but it doesn't send it anywhere. It doesn't send it to your fan motor, doesn't send it to your switches, doesn't send it to your igniter. That's when you're going to start looking at, okay, this is probably a board issue more than a component issue. So we've got a lot of different things that are going to be controlling these gas furnaces to make it so that we've got safe, proper ignition every time. And with the modern high efficiency ones, we want to make sure that it's not only burning, but that it's burning at the correct rate based on how much of a heat loss do I have, what's the load based on current weather outside, all that kind of stuff. All right, so here. All right. So common control sequences and controls. Again, there's 3 different ways that this is going to happen. So you've got 100% shut-off system, which makes sense as far as the idea and the name behind it. Makes both the pilot and the main gas valve will shut down in case of a failure. A non-100% is going to make the main gas valve shut down, but the pilot will continue to be fed gas. That's what can cause gas to leak out into a building without anyone noticing. That's not as popular because not as safe. So 100% shut off works pretty well. The best, though, and the most common, especially with an electronic ignition module or an IFC board, you've got it where the continuous retry is going to be what's going to happen. So if you unplug a gas furnace and you plug it back in, you will not start up right away. It will have a 90-second delay typically, at least. Now, depending on the manufacturer, the size of the system and everything like that, it can be a 90-second delay up to a 5-minute delay for a gas furnace. Most of the time, though, it's about 90 to 120 second. So about 1.5 minutes to 2 minutes is all it waits. And then the system will try to start up that sequence of operations, which I'm going to send out a video for today. That way you guys can see, okay, what is the sequence of operations and in what order are all my parts supposed to be turning on. So you guys can start, because if you know that sequence, if you really pay attention to that, that's all you need to know for a gas furnace. Understand how to troubleshoot the controls and the switches, and understand that order of operations or the sequence of operations, and that's going to cover everything you're going to run into. You will never have a gas furnace that you will not be able to troubleshoot. You might have some that still give you trouble, that make it tough, that aren't going to be easy. I don't doubt it. You're not going to be a gas furnace genius just because you know the order of operations, but it's going to give you a good foot in the door, all right? And the more that you work with these furnaces, the more problems you run into, that's what's going to ultimately make it so that you become a better and better technician when working on these systems. So just understand the continuous retry is your most common nowadays. Now, typically what you're going to see is most boards will allow for 3 retries, right? It will allow for the system to try and fire again in 3 times. That's it. After the 3rd time, it goes into a hard shutoff. It goes into that 100% basically. And then once it is at that 100% shut off, that's when we get the call, because the furnace was working. It sounded like it tried to fire up, but then it stopped trying. And that's when they're going to say, okay, I need an HVAC tech to come out because the AC's or the heat's not working. So this is a very common one that I've come across a lot of times, was gas furnaces in the wintertime. That would just, I mean, this is how you would get the majority of your calls, you know. And when an air conditioner goes out, an air conditioner's out. And you know in about 30 minutes. That's about it. You might give it a couple hours, you know, at most. Maybe it's just not kicking on yet. I don't know what's going on. You start messing with the thermostat. People notice right away, oh, AC's not working. The heat goes out, on the other hand, it's a little bit different. People might notice it. They might put blankets on. They're going to put on their electric heaters. They're going to just, you know, try to wait it out, you know, especially if it's towards the end of the season or the start of the season. Let's say late September to, honestly, right now, March, April. You know, this is the time of year where people could go without some heat, depending on how cold the day is, kind of thing. They might be able to get away with it. So, of course, not now anymore. People are going to notice that their heat goes out right now because everybody's stuck at home. That's a whole different thing. But yeah, it would you know, the call for the gas furnace, if anything, would be, you know, well, system was working, now it's not, you know, as opposed to air conditioners. It's like, well, it was working for the last couple of days and then it started slowing down. People keep real good track of how good that air conditioner is running, especially if they know it's a bad one or one that they've had problems with in the past, or that they know that I just live in an old house and it's going to have an old air conditioner. With gas furnaces and with heating appliances, typically it's going to be, you know, we waited until the last minute and then we just decided, yeah, I guess we should have someone come out. But these systems having it where they shut off permanently until someone comes out there, or let's be honest, until someone resets the system, right? You're wondering to yourself probably, well, if it's on 100% shut off, how do I get it to try and refire again? And all you got to do is literally unplug it, plug it back in. Genius. But because homeowners don't know that they have to disconnect the main power to their gas furnace, they're not going to understand that that's what that reset is there for. Now, does this mean that I unplug it, plug it back in, it's working? No. I unplug it, I plug it back in. Now I can watch it go through the order of operations again, and I can see where did it stop and where did it fail. And that's when I can start working on repairs and looking into seeing, okay, what's my repair? What's the problem? What am I actually going to be replacing or fixing on this system? Could just be loose wiring, could be a tripped high temperature switch that's just not letting the furnace turn on whatsoever. It could be that you've got, you know, a bad igniter or a thermocouple or a flame rectifier that's got a lot of soot built onto it, you know. So it's all sorts of things that can go wrong with them, but it's just understanding how to look for those, and then how to find them and everything like that. So again, lockout, like I said, time period to relight the pilot or main burner. You're going to have it where it'll be a soft lockout for a little bit. It'll try and relight, and then now some of them, like I said, it might do it 3 times and then go to a hard lockout. Some of them it's going to do 3 times, go to a soft lockout for an hour, then try again 3 more times, go to a soft lockout for an hour, and it'll do soft lockout 3 times and then do a hard lockout. So it'll try for ignition 9 times before it realizes, yep, I'm not going to get any ignition here. Might as well just get a technician to come out here. So basically, semi-shutdown, the module will keep trying to relight the system as the soft, and the hard is just literally it's not coming on. The system's got to be reset, and by that, power needs to be cut off, power needs to be cut on. Now that can be accomplished either at the furnace. Typically for gas furnaces, by code in most areas, you're going to have it where you have to have an emergency shutoff switch for that furnace. Typically, it's going to be, and I say typically because I've seen them in all sorts of locations, it's going to be somewhere, it's either mounted on the furnace or in that same room with the furnace. I've had it before where I had a house where they just moved in, and the house had just gotten checked out by a different HVAC company, and they said it was fine, and for some reason, hey, our AC is not kicking on, we don't know what's going on. And what had happened is, and I've talked about, we got furnaces and we got our air conditioner, they're going to be right next to each other together in our air handler inside. We're going to have that evaporator coil, our blower motor, our heat exchanger, all of them tied in right together. Well, they're also all going to be tied into the same control board, running off the same power source. So if you cut power to your gas furnace, you are also cutting power to your air conditioner and to your thermostat inside the building. You're cutting power to all of that. So when we have a, when I had this, what happened was the emergency shutoff switch for the gas furnace had been flipped off accidentally, because instead of being on the unit, like what would be logical, or near the unit in the room with a big red plate on it that says emergency shutoff switch, and it literally will tell you an arrow that says on in this direction and off in this direction. Really, they're foolproof systems. But instead, someone had decided, oh, I'm just going to make it look like a regular light switch on the wall on the second floor of the house. The only way I found out about it was asking the customers, do you have any switches that you don't know what they do? That was the solution. Do you have any switches that you don't know what they do? And then they were like, well, yeah, there's this one we don't. Flipped it on. That's all it took. I've had it before where, I had a customer one time, and luckily I was able to put the pieces together, because in her front yard, she had a sign and it said for sale, and there was an open house date, and it was this past weekend. So I go in on Tuesday. Saturday was when she had her open house. I went in on it was either Monday or Tuesday. I can't remember exactly. I get in there early in the week, and she's wondering, hey, what the heck's going on? My gas furnace was working all weekend, but then yesterday it started getting cold, and then, it just started the week. I thought I should call someone to get out here and get it looked at. What had happened? She had her open house. People had gone down to the mechanical room, which was attached to her garage, and it had a small amount of storage back there and everything too. And that's where their water heater, her furnace, her air conditioner, all that was in there. On the wall next to the door, as you walk out of the mechanical room, were 3 switches. 2 for the lights in the mechanical room, and 1 was for the furnace. The furnace one was not labeled for the furnace. So I explained to her, I was like, oh, this is a common thing. Don't worry about it. I'll put the switch on. I'll do a quick, diagnostic and make sure everything's working fine. But it looks like it was just, someone walking through the house literally just flipped a switch. They weren't looking because they're walking out the door. So they, it's just like you and I, we're walking out the door and the switches are right there. We're not going to flip the switch and then walk out. We're going to make our way out the door, have our arm back in there, flip the switches, and then close the door behind us, nice and easy. I'm not going to look at the switches. It's just switches. They're going to turn off the lights. If the lights are off, then it worked. you know. But if you've got 3 switches and only 2 lights, maybe pause for a second and realize, what's that 3rd switch for? Because there's only 2 lights and there's 3 switches. And that can only mean a couple of things. Usually in most, like in a bedroom or a living room or something like that, if you've got that kind of switch setup where it's 1's for the light, 2's for the light, 3's for the something, it's usually outlets. They'll usually, a lot of houses, they'll have the top and bottom outlets. They'll have the bottom outlet is permanently powered, and the top outlet, you have to flip a switch and then the power comes on. That's actually how my house is wired up for my bedroom and the guest bedroom are both wired up that way. I don't know why. Electricians can do whatever they want, I guess. I got no problems against it, but these kinds of shutdowns and shutoffs are what going to let us see where the system failed, because once we start it back up, we're going to see it start right from the beginning. It's not going to wear out our igniters. It's not going to wear out our gas valve by just, you know, throwing in gas that's not getting ignited constantly is not safe. That's one of the big reasons why we have these kinds of shutoff systems. So we don't have gas just constantly going. We don't have igniters constantly wearing out because they're receiving lots and lots of electricity and then doing nothing with it. So it just makes it so that we have our system last a little bit longer and it stays at the efficiency that we've rated it for and that we've gotten it, you know, that we bought it at. So purging the system, we've got a couple of different times it's going to purge. The pre-purge is when the system is right when it's starting up. All right. It's going to basically start, the inducer draft motor is going to start. It's going to start pulling air through that heat exchanger, through that S shape. It's going to pull it through there. And then it's going to say, okay, yes, we're able to get flue gases out. Let's keep them going. All right. So there's the pre-purge that's going to start when, if a system failed ignition previously, then the first thing that's going to happen is there's going to be a longer period of time that inducer draft motor starts up. It's going to take a longer amount of time to make sure, yes, we've got everything out of this heat exchanger. There is nothing blocking or nothing in there anymore. Everything, if there was natural gas in there, it's gone. If there was flue gases, it's gone. That's what it's trying to prevent. Interpurge, again, operation for certain periods of time, where it'll just turn on for a short period of time. The big thing is the post-purge. After the heating cycle, our burners will turn off. Our inducer draft motor will remain on for a post-purge. It will continue to get all the flue gases out of that heat exchanger and get them all the way out of our building. That's what we're trying to do this whole time. The way that this does it and the order that it does it is all determined by that IFC, by that furnace control module that you're going to be seeing. Those control boards are going to do everything for this. All right. So terminal markings and abbreviations. MV, main valve, pilot valve, main valve, pilot valve. Usually you're not going to see any of those because a lot of systems don't have pilots anymore. You're just going to see GB or gas valve. GND, ground, 24 volts. You guys know what 24V is. It's 24 volts, and then 24 volts to ground. THW might be one that you're not used to seeing. That is going to be for your thermostat wire. All right, the reason why it's W, because it's white, because that's the call for heating from our thermostat. Always going to be a white wire from our thermostat. As far as residentially, and as long as people wire it up properly and all that kind of stuff, I'm not going to say every time it's going to be that way. But typically white is your residential call for heating. Igniter or sensor, sense, spark, all these again, typically you're going to be reading a wiring diagram, getting a schematic of some sort, and it's going to tell you what these different things are going to be. They're going to allow you to basically, it'll have a key that'll let you know what all the different symbols and all the different abbreviations and everything like that mean and calculate out to. So it just makes life a whole lot easier. But, you know, again, igniter, sensor, sometimes they're going to be a combo part. Typically not so much anymore. Spark ignition, you know, it'll be your spark igniter or whatever. Let's So other things we've got new to the systems nowadays that is really cutting edge for these high efficiencies is smart gas valve. A smart valve is a gas valve and electronic control module in one. This is pretty much every gas valve nowadays. Well, not every gas valve. It's a lot of gas valves are getting to be this point now where they're going to be controlled. They can actually use it where they have small quantities of gas burning. They can control the level of gas burning in the system much more precisely. So you can have that variable control and speed in production of heat. You don't have it where, currently most systems, what it is if that furnace is starting off, if it's going to produce the same amount of heat, whether it's in October or whether it's in January, it's the same amount of heat it's going to try and produce. But if we have it where we can control the amount of gas being burned, the airflow and everything like that, then we can make it so that, well, January we'll go full speed, but October we'll only be burning about 50% of our fuel. We won't be needing to go nearly as high a temperature or anything like that. So that way when you have, a warmer day or something like that, it's not a big cost to your heating system. Let's say it's 65 out and you want the house at 68. But every now and then it's dropping down to like the 50s, so you just keep the heat on. Those 65 and those 50 days and those even down to like 32 and 30 and 25 degrees outside, it's still running at the same level of efficiency. Still got that same AFU rating, but now it can just control more aspects of its combustion process and its heat production. So that's pretty much everything we've got for our high efficiency gas furnaces. And remember, again, high efficiency furnaces reduce outdoor air filtration and room depressurization, where we can have it where it's going to be more of our combustion air is all of our combustion air is coming from outside to the inside. We're not losing any of that heat that we've just generated by turning it into combustion gases or combustion air. Because when we do that, that's when outside air will infiltrate. So all forced air gas furnaces have efficiency ratings. They do. That is one thing I can say in all four. All of them have some sort of efficiency rating at some point. Now, there's going to be a student that's going to come back in like a year or something like that and it's going to say, hey, I just found a gas furnace from 1962 or whatever, and it had no AFU rating or anything like that, and I tried to look it up and it didn't have one. I'm like, okay, well, fine. There was one. But from what I know and from what I've seen, pretty much all forced air gas furnaces will have an efficiency rating. They're going to have that AFU, annual fuel utilization efficiency. That's what that stands for. That's what we're talking about. So, again, remember, electronic ignition control modules and IFC boards. That is how we're getting our controls done nowadays. That's how we're getting our systems to turn on, turn off, and operate safely. So that's it for today. I'm going to send out a couple of quick videos to help you guys out with a few little concepts here and there. But other than that, I will post this video on YouTube. I will send out the links for this as well as other videos. And I will see you guys again on Friday. Have a good day.
You too, man. You too.